Cool. So today we're going to talk a little bit about inotropy, lusitropy, and chronotropy. So, I guess to start off, what do these terms mean and what do they do? Well, inotropy is, or inotropic effects are things that affect the contractibility of our heart muscle or the contractibility of the muscles of our different organs or different parts of our body. Well, lusitropy is the duration of these contractions, while chronotropy is specifically for our heart, the heart rate. And we can affect these things by doing a couple different things. Well, big one is the B1 or beta 1 cells when they come in and come into our heart. They can cause a couple different things to happen according to what they bind to or affect. So I guess the first thing that we can look into is what happens when beta 1 comes in and causes an inotropic or lusitropy effect. Well, when beta 1 comes in, it causes alpha 5 subunit to appear, which can branch off, but we'll talk about that branch later. Down the normal path, after the alpha 5 happens, it causes adenyl cyclase to increase in our around our heart, which causes cyclic AMP or CAMP or CAMP to increase in our body, and that causes protein kinase A or pKa to also increase, which allows us to phosphorylate in 4 different ways. First one is it can phosphorylate to our L-type calcium 2+ receptors, or to the channels, which would cause an increase in our calcium uptake, or an influx in our calcium here, as we can see, which increases the amount of calcium that we also receive from inside the SR into the ICF. If we take a look at this picture here, this is what we're talking about right here in the SR. So when pKa phosphorylates with these L-type calcium channels, it causes calcium to come in more. So now we have a lot of calcium inside our ICF, or our cytosol, as we say it. And this also allows more calcium from inside this area, from inside the SR, to want to come out. And this causes an increase of the amount of calcium released to our cytosol. Well, what does this do in the long run? Well, it increases our inotropy, or the contractibility of our heart. And just like that, when pKa phosphorylates into the RYR channel, which we can see the RYR is right here by the SR, and when it phosphorylates into it, it allows for a dissociation from calcium from the RYR receptors, which allows it the RYR to open more often, or the probability for it to open to increase, which allows the amount of calcium to come in from the SCR, or to be released from the SR into the cytosol to increase, which is again going to cause an inotropic effect, or an increase in the contractibility. Now, what else? What happens when pKa phosphorylates into things? Well, if you phosphorylate into phospholamban, you will increase the circopump activity, which is the circopump here is actually the opposite. It does the opposite to our calcium, makes it come back into the SR. Well, this does 2 things. One thing that this does is it increases the amount of calcium being reuptaked or being returned from the cytosol into the SR. So that means less calcium here, which means that we're not going to contract as long, but it also increases the amount of calcium here ready to leave the SR again, which, as you can see, means that we have a little path here, allowing this amount of calcium that's stored to move directions towards a calcium release from the SR into another inotropic effect. But if we just reuptake the calcium, that increases the speed of our relaxation as we're have less calcium to bind to troponin, and allowing them or troponin C, allowing less myosin heads to bind, as you can see here. When calcium comes and binds to troponin C, as we looked at in the last section, it causes the myosin heads to be able to bind to actin sites and release the ATP from, or the ADP and the phosphate from its body, known as power stroke. And this is something about smooth muscles and also just muscles in general. Skeletal muscles also work the same way, but smooth muscles can just do the process a lot faster. But this is what calcium does to being in the cytosol. It allows for this power stroke to happen, and so it causes the heart to contract more often. And so, since we're uptaking the calcium into the SCR or the SR, we're having less calcium out here, meaning that we're going to relax a lot faster, meaning that there's going to be the duration of contractibility is going to decrease, and this is known as a lusitropic effect or lusitropy. And now, if PK phosphorylates to troponin C, similar things happen. When it binds to troponin C, which is here, which is on this G-actin binding protein, it causes your calcium to not be able to stay bound to troponin C as long, and so the off rate of calcium from troponin C is that off rate is increased, which means that there's going to be calcium influx again into our SCR, as it's no longer going to have a place to stay, and this causes it to return here and causes the speed of relaxation to increase again, and lusitropy to increase, or contractibility time to decrease. And now, what about these two flow charts? Well, this is for chronotropy, or chronotropy in two different forms. Chronotropy, there's positive and negative effects. Here we have the positive effects to the catecholamines, or known as norepinephrine, and epinephrine. Well, over here we have acetylcholine. Now, before we move on, I'd like to talk about what acetylcholine does for our bodies. Well, acetylcholine is a neurotransmitter that sends boings or action potentials throughout our body, so that we can be able to, as more specifically in our muscles, so that we can contract. And acetylcholine in our skeletal muscles, actually, they're used a lot, and also in our smooth muscles, to cause calcium to influx in to the cytosols, so that we can be able to contract longer or more times. And so there's actually a negative effect that happens with chronotropy when M2 muscarinic receptors bind to BY heterodimers or alpha subunits. So let's start with BY heterodimers. So when they're bound to the muscarinic receptors, or the M2, this causes GERK or G protein rectifying or potassium units or channels that you can kind of find around here. They're channels that rectify the potassium, as it's said. That's what the K stands for. And they kind of release potassium from the inside of the cell to outside to the ECF or to the extracellular fluids, so that we can better our membrane potential or balance it out, so that we could go back into relaxation if need be. And so when this GERC opens up, it's going to cause our membrane potential to become more negative by releasing potassium outside into the extracellular fluids. And this is going to cause our heart rate to decrease. That was a very bad arrow down. Yes. And so just like during this flowchart style over here, when the M2 binds to alpha subunits, they cause a decrease in our cyclic AMP, and sometimes it can decrease our IF channel, which would cause the steepness of our action potential. So we have like a chart here of, like, let's say a algorithmic cell. Here we have section 4, section 0, section 3, section 4 again, 0, 3. Well, it's going to cause the steepness of these to become less steep or flatter, so it's going to end up kind of looking like it's not going to go up above the potential or the membrane potential for as long, or it's also going to take more time to hit membrane potential, and this is going to cause our heart rate to decrease. And similarly to that, it can also, the cyclic AMP being lower in the body will cause our eye calcium channels to decrease, which is the amount of calcium that comes into the cell from, or into the ICF from the S or from the L-type channels, and this is going to decrease our heart rate as well. And so those are the negative effects of chronotropy on acetylcholine. Let's talk about the positive effects. Well, the positive effects are that happen with non-epinephrine and epinephrine, or the catecholamines, is when beta-1, as we know from this place over here, it increases our adenyl cyclase, which increases our cyclic AMP. Now, increasing the cyclic AMP can also increase our sodium influx, which will increase the steepness of our slope, or cause membrane potential decay to occur, which what membrane potential decay does is it allows us to stay higher in action potential for longer periods of time. And so since we're talking about sodium here, we're actually talking about normal cardiomyocytes and not algorithmic cells. So the little chart would look more like 2, and here you have section 4, 0, 1, 2, 3, and then 4 again. Yeah. And so this is increased by the amount of sodium that's added in, and that's what increases the slope right there. And so adding more sodium here will increase the slope even more for our cardiomyocytes compared to our algorithmic cells, which open up from HCN or acetylcholine funny type channels. And so what else happens? When cyclic AMP increases, it also increases our pKa, as we talked about over here, protein kinase A. And so when protein kinase A increases, it increases our influx of calcium, as we've seen here in the Inotropy Lusitropy chart. And so as we increase our calcium, or the influx of it, it also increases the steepness of our slope, which increases the HR, or the heart rate. And so as we talked about here, in this case over here, the GERC will, or closing the IF will cause a decrease in our slope, while over here, having more calcium will increase the slope of these algorithmic cells, which will make them be a lot I'm kind of bad at this right now, but you get the point. They will increase the amount of repetitions that these algorithmic cells can occur in, which, just so we set clear, examples of algorithmic cells would be our SA node and our AV node, which are the start of depolarization of our heart. And so that's why it's very important. So increasing the steepness of this means that it will be depolarizing the cell more often, and we'll be able to have an increased heart rate because of that, because we'll be contracting more often. Same for the increase of calcium will also make the threshold more negative, meaning that it's going to be easier to reach threshold. Because on a normal chart here, this is like negative 70 or something like that. And so if we make it more negative, like let's say bring it down to negative 90, we'll be hitting action potential more often, which means that we're going to contract easily or more easily, which will increase our heart rate. So what did we learn today? So for a brief recap, we've learned that beta 1 will increase our heart rate, can increase the contractibility of our heart, decrease the duration of these contractibilities so that they can happen a lot quicker. But for if they bind with acetylcholine, it'll actually decrease our heart rate instead. And we learned that this happens through the effect of calcium coming in and out of our cell from the extracellular fluids and from the SCR into the cytosol. And these effects are regulated by these three types of effects into our body. And thank you. That's all for today.